Hello everyone, welcome to Programming Knowledge. So I again welcome you all to Programming Knowledge. So this is the third tutorial of our competitive coding series. So basically today what we are going to cover the number theory part 3, that is primality test. And basically in today's tutorial we are going to compare the primality test in O of n complexity versus O of root n complexity. So this basically we would start with the coding part, and here you can see that on the right side I would write the code, and on the left side I would show you the output of the code. So basically, what are prime numbers? Prime numbers are those numbers which have two factors. So basically they have two factors. One is the number 1 and the number itself. So number itself is the second a factor of it. So basically, they have two factors. One is the numeric one, and then another is the number itself. So how can we find the prime numbers? Basically, we can start with two approaches. One approach is this one, approach one, that we find the factors of the number and then we check for it. So we can do it in O of n complexity. Okay, and another approach I will tell you, that is an efficient approach. So basically that is efficient approach because it helps you to cover the base cases, plus approach 2, which I'm going to tell you, and it helps you to cover the base cases, and it also gives you the hint in O of 1 complexity. So base case plus hint O of 1 complexity. Then if we proceed with that approach again, we further proceed with that approach, so we at most get a cost of O of n, O of root n complexity. Basically we would get the base cases plus hint in O of 1 complexity. So if we are able to proceed with that, if we get a result with that, so basically we would cover with that in O of 1. If we further proceed, then at cost of maximum cost of the function would be time complexity would be O of root n. Okay, so that's pretty good in terms of efficiency with respect to approach 1. So primality test is very important. So let's get start with this. So define, uh, I'll type what let me type approach 1, and I would pass this, and next I would define is approach. Okay, I would even pass this, then we would complete these functions. So let's start with this. So what we can do test cases is int input, then we can have a while loop for the number of test cases while t is equal to t minus 1. Then we would have a number here, we would have a number with us, that is n is equal to int input. Okay, so we would take the input, then we would say print approach 1. Okay, I would correct the above function statement, approach 1 of n, then print approach 2 of n. Okay, so for this, let me do this. This should be an n, this is 2, and this is 1 and n. So let's get start with the approach 1. So for that you can see that we have approach 1 here. So what we can do, so we take divisor count, let divisor count is equal to 0, and that for what we are going to, for I in range 1 to n plus 1. So basically we for loop from 1 to n. So basically these are closed brackets, that means that is inclusive in nature. So if n modulo I is equal to 0, okay, then what we have count plus equal to 1. Okay, so if n modulo I is equal to 0, then count plus equal to 1. So basically we are going to increase the diff count plus equal to 1. Okay, so when after the getting the diff count, divisors count, so basically we need to check that only there are two factors. Mainly there are two divisors. If diff count is equal to 2, then return true, yes, else return false. Okay, so for this and before this I can add a statement here, int diff count. Okay, so let me check with this and let me run this function. I'll for the timing I'll comment this out. So yeah. So I'll start with the split screen. Yes, so I'll take 5 test cases. Let me take 2 test cases. Let me type 12. So 12 has 6 factors. So let me check. Factor is 1, then another is 2, then 3, then 4, then 6 and 12. Yeah, so these were the 6 factors in it. And let me type 5. So 5 has 2 factors, that is true. So let me run it again with few more test cases. I'll take 3 more test cases. One is 23. So yes, 23 has 2 factors. So yes, it is a prime number. 1 and 23 are the 2 factors. Then let me take 24. 24 has 8 factors. That is 1, 2, 3, 4, 6, 8, 12 and 24. Yeah, those are the 8 factors. So let me take another number. That is 53. 53 has 2 factors, so it has a yeah, so it is a prime number. Yes, but I'll have a efficient approach than this one. What you can have on your side, that you can see this is going to be some efficient approach. So I'll comment this out. Now I will go with the another approach. First, I'll cover the base cases. If n is equal to 0 or n equal to 1, so uh, return false. So how much time complexity does this hint take? This takes a O of 1. Okay, then if n equal to 2 or n equal to 3, this takes again O of 1, big O of 1 time complexity, because all the operations or if conditions only take O of 1 time complexity. So basically here you can see that this can be done in O of 1 time complexity. So next I would go, then return. So this would be a, so because basically 2 and 3 are prime numbers, so we would return true. Okay, now another operation we are going to do in O of 1 time complexity is this one. If n modulo we know, if n modulo 2 is equal to 0 or n modulo 3 is equal to 0, then we know this won't be a prime number. Yes, so this won't be a prime number. Any number divisible by 2 or 3 won't be a prime number, because any number will be divisible by 1 and the number itself, plus it has 2 divisors till now, plus if it is divisible by 2 or 3, then the divisor count becomes 3, so it won't be a prime number, so we would return false. So this was I'm talking about. I was talking about these 3 base cases plus hint, that these are done in O of 1 operation. So basically O of 1, O of 1, then again O of 1. Even after this, if we don't get our desired result, if we proceed with this, so we only get O of root n complexity, and I will I will show you how. So I'll do, from math import star. Okay, and I'll share a for loop for I in range. So after 2 and 3, which is the next prime number 5. Okay, then sqrt square root of n, square root of n, and I will take it as a floor. So I'll do int, or you can do floor. Int square root of n plus 1. So this would for loop from 1 to root n. Okay, then if n modulo I is equal to 0 or n modulo I plus 2 is equal to 0. So basically, if you start with 5, like the same condition goes, like 2 was the first prime number, then 3. So we checked for 2 and 3. But when we start from then we have already checked for 2 and 3, we start with the next prime number, that is 5. When we start with the 5, then we start with check with for the 5 and 7. Then again something like this, because we check with 5 and 7, we're trying to again make a relation in the such a way, if this is 0 and even this is 0, then we would return false. The same case, what I'm explaining with the base case, like for the one we did with the 2 and 3, like first 2 is the first prime number and 3 is the next, then return false. Then we'll start with the next prime number, that is 5. If n modulo I, that is 5, and modulo I plus 2 is equal to 7. If divisible by 5 and 7, then again return false, because already a number would be divisible by with the 1 and the number itself. And if it is next divisible by either 5 or either 7, then diff count is equal to 3. Then the diff count is 3, then it is not a prime number, then we return false. And in the end, after so many conditions, if this doesn't work, then it is a prime number, then we return true. So here you can see, so this is a more efficient approach we have. So here you can see this is much of an efficient approach. So I would quickly give you from math we would import star, and we have used in square root, and this is the, so let me try this. I would comment this and now run the function. Okay, I'm having an error. Let me check. Def approach to. Okay, I would use this statement on the top. From math import star. Yes. So yes, now I can run. So I would take some test cases. Let me take 6 test cases. If I do 2, 2 is a prime number, 3 prime number, then 53 as prime number, then 8 not a prime number, then 24 not a prime number. Let me take another number, 19, yes, a prime number. So here we can see, check for the prime numbers. So basically, so this was the case where you can see that 53, I guess, yes, it is a prime number, because 53 doesn't have any factors. So yes, we are done with this tutorial. So this was an efficient approach to look for prime numbers. So basically, what I wanted to tell you, that approach 2 was approach 2 was more efficient. This is a more efficient approach, so you can carry on with this approach. So thank you guys, thank you so much. And then so we will carry on with the number theory in the next tutorial. Thank you guys.